Hi, my name is Christian Royer. My partner is Adana Anderson. Our advisor is Dr. Liz Schlemmer, and our topic is implementation of smart grid technology at Cal Poly. Background and motivation. Energy consumption in the U.S. will increase by 47% from 2010 to 2035. In fact, U.S. will produce 25% of the world's greenhouse gases, even though we comprise only 4% of the world's population. And our current power grid has not had many large-scale innovations for the past decades. What this boils down to is we are going to continue to use a lot of electricity, and we need to work on being more efficient with our energy usage. When you turn on a light switch, the electric company will charge you at a rate of whenever you turn it on. For example, if you use electricity during peak hours, you'll be charged at a rate that is higher than non-peak hours. Energy during peak hours is mostly generated using hydrocarbons and is rarely renewable energy. And during off-peak hours, there is not enough demand to meet the minimum output for an energy company. So basically, there's a lot of wasted energy during off-peak hours. Some problems with this is one, that is more costly, and two, that is also inefficient. If Cal Poly, businesses, and residential areas start using a lot of electricity during peak hours, the energy company needs to work harder to generate this electricity that is demanded. This can cause blackouts in the area.
For our project, Adana will be handling the implementation and design layout of the smart grid technology, while my part will be to design a tool that we'll be able to use to figure out when is the most beneficial time to release the energy for our storage devices.
Next, I'll be talking briefly about one way you can store energy with the smart grid. During off-peak hours, you will store the energy in a battery. This is because it is cheaper to generate electricity during off-peak hours since there is less demand. Then during peak hours, you will release the energy from the battery and start using it for any appliances or other electricity needs you have. This way, you are using the energy you created during off-peak hours, which costs a lot less.
Now, Adana will be talking a little bit about how the system works. Next, I'll be talking about the process about how we solve this problem. For this project, we use the plan, do, check, act process to figure out a way how we can make this smart grid technology work. So first we planned and we designed a system that can analyze different battery sizes. And we also wanted to create an analytical tool that can calculate the rate of return for investment in whatever battery technology we choose. So to do this, first we had to collect the PG&E data rates of how much PG&E charges Cal Poly, and then we had to find the Cal Poly energy usage data rates. From there, we had to check our data and analyze any kind of trends or usage anomalies that we notice in any of the energy rates. And then from there, we would develop different kind of forecasting methods to use and use that to figure out what is the best costing method to use. After this, we'll act and create a new present value for whatever investment would be the best one for us to choose from. During the planning step, we need to figure out what battery size we were going to use. So this will pretty much represent the cost of the system. So we chose two battery sizes that we feel would be able to handle a significant load from Cal Poly's energy usage. One would be 1500 kilowatts and the second would be 5000 kilowatts. And then for our system design, we had to figure out what was the best system to release this energy. And then we came up with three possible choices. A 2-hour peak, which basically means looking at the 2-hour peak of whenever we use the most energy, using it during the entire peak hours, or estimating the peak of when it's going to be. And I'll go into more of this later. During our do step, we had to get to gather the necessary data we needed to use for this energy storage problem. So looking at the PG&E rates, we try to figure out what was the highest amount of impact that we can make. So for energy usage, you can get charged for summer and winter rates. In addition, you'll be charged a demand charge and an energy charge. As you can see below, a max peak has the highest amount of energy cost at $14.03 per kilowatt, and if you're able to reduce this and use it during part peak, it's only $3.04. So that'll be one major goal that we're trying to accomplish. Next, we check the Cal Poly trends for Cal Poly's energy usage. We were given a time period of June 2011 to July 2012 for the amount of energy that we use at Cal Poly. This gave us 35,000 data points in an Excel file that I had to reduce and find trends for. So what I did was I looked for daily and monthly trends to see when were the max peak hours and when are we using the most energy. From that data, I was able to see that 90% of our peak demand charges were actually during max peak hours, which was good for us because we wanted to reduce those costs and we'll see a significant cost savings. But every month was a different amount. As you can see in April, the majority was during 1 p.m. and 2 p.m. according to military time. But in January, you can see that the monthly peak is mostly around 5 p.m. So the trends depend on the time of month, and this could be because of the weather, the time that the daylight is out, and other various reasons. I also looked at weekly and daily data trends. As you can see, the data mostly follows a cycle. It'll raise up and then raise back down. And during the month of October, this peak mostly happened around 2 to 1 p.m. So I had to look at each month and see when the average peaks were happening. After analyzing these trends, the next thing I tried to do was find the right way to release the energy. In this example, I released the energy over a 2-hour period. I charged the batteries from 1 a.m. to 3 a.m. because during off-peak hours you're not charged a demand charge. And then I released the battery during whenever we forecasted the peak to be during this month. So in this example, in October, I forecasted the peak to be between 1 to 3 p.m. Next was a whole peak reduction. I charged the batteries during the same time, however, I released it during a whole 6-hour max peak period. As you can see by here, the graph looks really low, so let me blow it up for you. As you can see, the usage went down slightly, but it went down slightly for the entire peak, causing a lower demand charge usage. Lastly, we did something called estimating peak. What this does is that it will automatically adjust itself to know when the max peak is happening, and then it will start releasing the energy right away, thus lowering our demand charges. This would be pretty much a perfect system model where we would automatically know when it's going to happen, so there'd be no forecasting. After applying these different type of releasing systems, I was able to calculate the annual cost savings over a year period. As you can see in the 1500 system, the one that would save the most amount of money would be the estimating peak if it would automatically be able to adjust itself with 300,000 in savings. But if you use a 2-hour peak, which is possible to do, you would save around $200,000. However, in the 5000 system, you'll save most of your money again during estimating peak, but releasing your energy during the whole peak will save a large amount of, well, more than the 2-hour peak. This is because during saving energy during the whole peak will reduce all the heights on the top, which will reduce your demand energy charges. So if you're releasing a small amount of energy, it's going to have a less amount of effect on your demand charge. But once you get a bigger system, you can effectively lower the entire demand charge. Looking at our net present value after 5 years with a 6% annual interest rate, you'll be able to see that estimating the peak would save the most money. However, this would have to be a perfect system that would know exactly whenever any peak was about to happen. So a more realistic approach would be to either use the 5000 system for a whole peak approach, or to use a smaller system for just that 2-hour window. But according to Black & Veatch Corporation, the capital costs for high storage batteries are estimated to be around $4,000 per kilowatt, which would be respectively $6 million and $20 million for each of these systems. So as you can see right here, you're not saving enough money to pay back that entire system. But even though you're not able to pay all that money back, you're able to save a lot of stuff for the environment and other energy costs that aren't recordable. So things that need to be future studied for this project would be the environmental impact and see how much of a carbon footprint we're reducing at Cal Poly by using energy during off-peak hours, so that way the energy company doesn't have to ramp up their production during peak hours. We'd also need to see where you can store all these batteries, because to save such a large amount of energy will use a lot amount of space. We'd also need to look at our proof of concept system and see what kind of energy efficiency issues that we'll run into. Thank you.